welcome to this video in which we resume our discussion about functions. So in the last part, we defined the function as a mapping or an assignment or a transformation that maps every element in a certain set A to exactly one element in B. We insisted on this fact for the function to be, for the mapping to be called a function. And we said that we have to look at this side and we have to make sure that if we represent the mapping as arrows going from the elements of the first set towards elements in the second set, we should make sure that every element has exactly one outgoing arrow. So it's sufficient to look at this side. If we see an element without any outgoing arrow, then we say that this mapping is not a function. And if we see any element with two different outgoing arrow, we don't care where they are heading, we would say that this is not a function either. Okay, so every element should be mapped to one and exactly one element in the other set. We also explained how this can be seen as a subset of the Cartesian product of A cross B, so that every element A is coupled with its image f of A, which we call here B. The first element comes from A, the second one comes from B, so this is why it's a subset of the Cartesian product of A across B. So you would see that if we learn more about relations between sets, that relations in general are defined in this way. They are subset of the Cartesian products between sets, and functions are particular relations where actually every element of A appears exactly once. Okay, so no two elements of the relation have the same first element coming from A. We also reviewed certain naming conventions. So we say that F maps A to B or is a mapping from A to B. We say that A is the domain, B is the codomain. If F of A is equal to B, then B is called the image of A under F, and A is called the pre-image of B. The range of F is the set of elements in B that have pre-images in A, or the set of all images of points in A. We denote it in this way, F of A, and you should, when we write F of a certain set A, you should imagine that this is a subset of B. It could be equal to B if all the elements of B are engaged in a certain mapping or relationship to elements in A, or simply a subset of B. So we can also define the function f partially on any subset S of A. Okay, so and in this case we would also obtain potentially a set of elements in B that represents the set of all the images of elements in S particularly. So clearly this is part of the range of F, which is itself a subset of B according to this definition that we have on this slide. Two functions are equal when they have the same domain, the same codomain, and they map each element of the domain to the same element of the codomain. Okay, good. We started considering a few examples. So the example of mapping countries to their default currency. Well, this is a function. So just to show you that functions are not necessarily arithmetic formulas, actually, that of the form f of x is equal, I don't know, like x squared plus 1, or x plus 1 over 2, or whatever. So we can accept, even if we're working with discrete mathematics, we can accept functions like this, of course, and we can use formulas to denote the relation between the elements of the set of real numbers or natural integers and themselves, or other sets. But we can also have discrete sets, such as here the set of countries and the set of currencies, and the relation between them that actually is a function, because if we look at this side, we have exactly one outgoing arrow from each element in this set to the left, okay, going to certain element in the right. We don't care where this is heading. Well, if you consider the mapping the other way around, so yes, this is a function, but if you consider the mapping the other way around and you look at this side, um, so you see some exceptions. So you see here that certain currencies are mapped to more than one element. So this is why this function here or this mapping here is not considered a function. But yeah, we can actually make it a function if we group the countries with respect to their used currencies. And in this case, this big set here that contains set of countries and whose elements are sets of countries who share the same default currency, such as the European countries. Well, in this case, the mapping would be a function. And even we will end up having a bijection. We will talk about this in a couple of slides. So to represent functions, we can define them with explicit statement of such as the assignment of students to grades to students, or the country currency example, and this works perfectly when you have discrete sets. But we can also use mathematical formulas, and in this case, it depends on the domain, but we can apply it to discrete domains or enumerable domains, such as the set of nature integers, or all integers, or real numbers, or complex numbers, or whatever you want. You could also define it on vectors, for example, coming from Rn, Zn, or whatever you want. It can also be seen as a computer program, actually, or particularly a computer function that maps input of a certain type to output of a certain type. And the link between the input and the output would be the code that is written inside that procedure or function. We will learn more about coding and functions and procedures in programming in the algorithms chapter later on. So we have this example here. We have these two sets, A and B, and we have a mapping between the elements of A and the elements of B. So now we can answer these questions. What is the image of A by this function f? So the function f going from A to B is depicted in this diagram or picture. So you can pause the video after each question and then try to answer it on your own. I will go a bit quickly on them to start the new part about properties of functions. So f of A is clearly Z, so it's the element in B that is mapped to A. The image of D, it's the same thing as answering the question, what is f of D? So it's equal to Z2. The domain of f, clearly, it's the set where the arrows are outgoing to the other set. So it's A. The codomain is where you have incident arrows. It's B. The pre-image of Y, it's it could be a set, actually, okay? So it could be the set of all the elements in A whose image is Y. So here we only have B. F of A is the subset of elements of B that have pre-images in A. So it's Y and Z. And the pre-images of Z actually are more than one. They are A, C, and D. So it's a subset of A. Good. So we can also define, as I told you, a function partially on a subset of the domain. And then in this case, f of s would be a set of the images of the elements in S, okay? So for example, f of ABC alone is actually Y and Z. And the f of C and D is the singleton element Z. Okay, so in the upcoming part, we will be talking about types of functions, namely injective functions, surjective functions, and bijective functions. So some functions happens to be injective,
Some others happen to be surjective, and some of them happen to be both. In this case, we would say that it would consist of a bijective function. And we will see that a part of the fun of using or applying these definitions is to prove them for certain functions in the practice set of exercises about sets and functions. But later on, we will use this concept in the so all of them may occur in exercises about logical proof of a certain function being injective or surjective or both. But we'll particularly use the concept of bijective function to reason about the cardinality of sets in the next chapters. Particularly infinite sets, countably and uncountable, countably infinite and uncountable sets. On the other hand, we will learn about composition, and this means the application of a certain function f on the images of a certain function g being applied on certain elements x. So we can talk about the f of g of x, something that we denote in this way, g round or circle g. F round g. So f round g of x is nothing but the function f being applied on g of x for every x in the original domain. So we'll learn about this, and at the end we will also have, so this is part 1, part 2, and at the end we'll talk about certain particular functions. This would be necessary for some exercises currently, and later on we will see them when we talk about algorithms, namely the floor and ceiling functions. Maybe you know them already, but we need to make sure that it is common knowledge for everyone. We'll also make a quick recall on factorial functions. Okay, so the factorial of a certain integer n, and then the piecewise functions really towards the end. Okay, so let's start with the first part. A function f is said to be one-to-one or an injection if and only if f of a is equal to f of b implies necessarily that a is equal to b for all a and b in the domain of f. Okay. So it has nothing to do with this image. So for example, the mapping that you see depicted here to the right is an injective function, because every element here has a different image in B. Okay, so maybe you would say that you mentioned nothing about different images. You use this definition that if f of a is equal to f of b, then necessarily a must be equal to b. But if you look at the contrapositive of this implication, it's not q, so this is p implies q, and not q, which is if a happens to be different than b, then necessarily what? Necessarily f of a must be different than, I'm sorry for those random horizontal lines, must be equal to f of b. Okay. Of course, for every a and b and in a. Okay. So yeah, if you look at this element and this element, they have different images. The first, second, they have different images. The first and the last, they have different images, both for BC, BD, CD. Okay, so if you pick up any couple of different elements, their images are necessarily different. In this case, the function is called one-to-one or an injection. Maybe one remark about injections. To make sure that every two different elements in A have two different images in B, well, think about it. You need as much as element in B as in A, so at least as much as elements in B as you have in A. to accommodate all the elements of A's with images to them. Okay, so we can compare the size or the cardinality of A with the cardinality of B. Okay, so think about it. Which one must be greater than or equal to the other one? Okay, so of course we can have them equal because you will have enough element in B to accommodate the elements of A. But yeah, as here, you can have some more elements in B, no problem. But at least you need as many elements in B as you have in A, okay, to accommodate all of them with different images, okay, from B. Good. What about surjective functions? Well, f is called onto or surjection if and only if for every element B in the codomain B, there is an element A in A. So where f of A is equal to B. Okay, so every element in B has a pre-image. So if you look at at this mapping here, well, this function is not surjective because V is not busy. V has no pre-images in A, okay? It has no incoming arrows. It has no incident arrows. So to check that a function is injective, okay? By the way, yeah, this is another thing to say about injective and surjective function. Let's say it about injective functions. You have to look now at this side, okay? So to check whether a mapping is already a function, we looked at this part, okay? But to check if a function is injective or surjective, well, we have to look at the right-hand side. If you see more than two incident arrows coming to the same element, okay, then this means that two different elements in A have the same image, and in this case, the function is not injective. But in an injective function, you have only one incident arrows, one incident arrow. Well, this is at max, okay? Some of them have zero incident arrows, no problem, okay? The function is still considered an injective function. But what we are saying here with surjective functions is that every element in B has a pre-image in A, okay? Well, at least one. So some of them, such as Z, for example, it has two different elements, two different pre-images in A, okay? No problem. But at least it's busy. It has certain pre-image in A, okay? It's mapped to something in A. So this function that we have in this slide is surjective. It is not injective because we have more than one incident arrow into one of the elements of B. So it means there exist two different elements, namely A and D, whose image is the same. It's Z. They are not different, okay? So so clearly we have to look at this side, and if we try to compare this time the size of A and B, well, clearly you need to have the size of A to be greater than or equal to the size of B, because you need as many elements in A as you have in B to keep all the elements of B busy, to map them to certain pre-images. Okay, so you need as many elements in A as you have elements in B to provide pre-images to those elements in B. Okay, if it is equal, then it's fine. It's not a big deal. Okay, and I think you start noticing that having a function that is both injective and surjective is about having the right balance. It's about having A and B with the same size of elements, okay? So you cannot create a function that is both surjective and injective, which means it's bijective, unless you have the same size, the same number of elements, because every element in A is already having a certain image in B. You want to make every element in B an image of a certain element in A, but it should be an image of a different element from A. So if you add all these constraints, then you end up having the size of A equal to the size of B. And this is why I told you since the beginning that we are going to use the notion of bijective functions to talk about the equipotency of sets, the equal number of elements in sets. So yeah, a bijective function is both one-to-one and onto. Okay, so this is why there is no more to say about it. It's the end of the definition of surjective and injective functions. Well, this one is a bijective function. Even if we spread the elements of B a little bit, but all in all, we have 4 elements here and 4 elements there. Okay, so if you add 1 element here in B, then you risk having ending up having a non-surjective function, because there is a certain element in B that has no preimages in this case. If you add 1 element in A, then if you keep it without an image in B, then you end up having a mapping that is not a function in the first place. Or if you want to map it to some elements to an element in B, well, you end up with 2 different elements in A having the same image in B, and which makes the function non-injective. Okay, so you cannot add any element anymore to A or B, or you risk making the function non-injective or non-surjective, which means not bijective or not a function in the first place. So let's talk about the technicality. How to prove that a certain function f is one-to-one? Well, you show that for an arbitrary x and y, if f of x is equal to f of y, then x is equal to y. And as I told you, you could also use the contrapositive. You can pick up 2 different elements, x and y, that particular elements x0 and x1, let's say, that you know that they are different, and then you show that f of x0 equal to f of x1, let's say, would lead to a contradiction, or that necessarily f of x0 is different than f of x1. Okay, so you pick up the method that suits you better according to the exercise and to the nature of the function f. Well, to show that a certain function is not one-to-one, is not injective, well, it's sufficient to show that you actually have 2 different. What's happening? I need to switch to the next slide. Yeah, so you need to find a particular couple of elements, x and y, such that x is different than y, yet f of x is equal to f of y. Okay. To show that f is onto, so you show that for an arbitrary y in B, you can find an element x in A such that y is the image of x. And so as if you prove this for any y in B, okay? And to show that it's a certain function f is not onto, it's not surjective, then you should find a particular element y that has no preimages. But once again, to prove this, you need to prove a certain universally quantified expression, which is for every x in A, that the image of that x cannot be equal to y. Okay, so we only have an existentially quantified expression when we want to prove that a function is not injective. Okay, in the case of a proof of an injective function, we need a universal quantifier. For the proof of onto, or the refutation of the proof, the onto property, we need universally quantified expressions. Let's consider a few examples. So if we have this mapping, maybe it's easier when we see it when we draw it. So I recommend that you do it for the other exercises if needed. So we have examples, I'm sorry. So we have f of a equal to 3, we have f of b equal to 2, and we have f of c equal to 1, and f of d equal to 3. So what this mapping, what can we say about it? So the question here is whether it's onto particularly. So what do you think? Just pause the video and think about it. Okay, so it's sufficient to look at this side here, okay, the right hand side, and to see that every element in this codomain, let's call it B, is busy with a certain relationship with an element from A. So it means that every element in B has a pre-image or for every element y here, there exists a certain element x in A such that y in B is equal to the f of x. So yes, it is an onto function because all the three elements of the codomain are images of elements in the domain. If the codomain is changed to 1, 2, 3, 4, well, this would not be the case anymore. Another example is the famous quadratic function f of x equal to x squared, where the domain and the codomain are the set of integers. So is it onto? Okay, so you have to look now at the y-axis, if this is the x-axis and the y-axis. So you have to look at the y-axis and to check if any of the elements on this axis has no pre-image. Okay, so how to do this? For example, for 100, if you do a certain projection this way until you meet the curve or that way, then you can find certain pre-images. Okay, at least one. So even if the curve was going that way, so eventually you would find one pre-image. But if you pick up minus 100 or minus 1 even, well, you don't meet the curve at any place. So there is no pre-image for minus 100. Okay, so when you have a graph, it's also kind of easy to check whether the function is onto or not. Not even talking about the fact that in this example they are considering the set of integers. Okay, so even if we restrict the so just let's answer the first one. So there's no integer x with x squared equal to minus 1. Okay, so minus 1 has no pre-image. Okay, what if we restrict the codomain to before r plus? Let's consider z plus. Okay, well, I think even if we restrict the codomain to this part here, to the set of positive integers, so it means that we take our function from z to z plus. Well, anyway, we cannot guarantee that it is a surjective function. Well, because certain elements like 10, for example, or 99, they don't have roots in Z. Okay, so they don't have pre-images. Okay, if we take it from R to Z plus, well, then it works. Okay, yeah. So it really depends on the case. Good. So what about this function and being one-to-one? The same function, x squared function. If we consider the set of integers this time. So I think that, think about it, please, and then resume the video. Yep, so you have to look at any value here and to see if it has more than one pre-image. Okay, so actually for every value that is greater than or equal to 0, you have two different roots or two different actually pre-images for that value. For example, for 100, both minus 10 and 10 are pre-images of 100. Okay, so imagine it this way. So you have minus 10 somewhere, and then 10 somewhere else, and so you have two different elements, and they are both mapped to 100. Okay, so clearly this function is not onto because we have two different elements, minus 10 and 10, whose image is the same. Okay, so so it happens that this function, particularly defined over the set of integers, is not onto neither one-to-one. And if we restrict now the domain and not the codomain to R plus, well, this changes a little bit because the curve is going from 0 upward, and now every time you make a horizontal line this way, you will only find one single value. Okay, because you're not considering the domain, you're excluding actually all the duplicata of values of pre-images. Okay, yeah, so by restricting the domain, as in the country's currency example, so when you restrict the domain of the codomain the nature of the function f would change, and even the mapping might not be a function, but then it becomes a function after you restrict the domain or the codomain. Okay, so another example, from the set of integers to the set of integers. Such that the function is equal to the function of x is equal to x plus 1. We want to answer these two questions, so try to answer them on your own and then get back to the video to see that, yeah, this function is actually both, okay, because no matter what the element n, you can find the element that is equal to that element plus 1, and no matter what element y actually that you consider on the set of integers z, we know that there is an x that is equal to y minus 1, such that f of x actually is equal to y. So for every y, there is an x. So we have to write it this way. Let's put it correctly. So for every y in z, you can find an x, particularly the x that is equal to y minus 1. So I could provide you with this as a function of y. So it always exists for every y, such that the f of x is equal to y, or y would be equal to f of x, because now if we add 1 to it, we will obtain y. Okay, great. So when you have such functions that are bijective, then you can talk about the inverse of the function f. Okay, so if f is a bijection from a to b, then the inverse of f, denoted by f minus 1, is the function from b to a, defined as f minus 1 of y, where y belongs to x, is equal, where y belongs to b, is equal to x, if and only if f is equal to, f of x is equal to y. This is what I use here actually, okay? In this function, I practically calculated, like, to show you that all the pre-images exist for any element y, I used the f minus 1. So we would draw it this way. We go from a to b using the function f, and for every element a, we have the image b that is equal to f of a. And in case the mapping, as I said, is a bijective mapping, the mapping is a bijection, it means bijective function, then f minus 1 exists, and f minus 1 of any element b would be equal to the element a, such that f of a is equal to b. No inverse exists unless f is a bijection. Quite obvious, but if you try to think about the reason why it is the case. So the key is that for f minus 1 to exist and to be a function, okay, to be a function, well, you need to meet this requirement that every element y in b has an image, and exactly one with f minus 1, have exactly one image in A by f minus 1. Okay, so this is like for f minus 1 to exist, it means for f minus 1 to be a function, we should meet this property. And this cannot be the case unless all the elements of B are involved in the relation with elements in A, and every one of them has at most one. So at least one and at most one, it means exactly one relation. So, so for this to happen, the original function f needs to be a bijection. So if we have f in this way, in this example, I think we saw it a couple of slides ago. Well, in this case, we can define f minus 1. It goes the other way around right now, and it maps the elements of B to elements of A. And now we have this like 1 to 1 and onto mapping. Great. So what if we have this mapping from ABC to 1 to 3? Well, is f invertible? And if so, then what is the inverse? You can do it on paper, I think. If you draw it, you will see it. So yeah, the function is invertible because it's a bijective function. And f minus 1 of 1 is equal to c, f minus 1 of 2 is equal to a, and f minus 1 of 3 is equal to b. Another example here, so that we have discussed so far. So in this case, the function is invertible, and f minus 1 of y is equal to y minus 1. Okay. So I agree with you that sometimes, even if the function is not bijective, we can talk about the inverse or the reverse of the function. I don't know how to call it because we already consumed the definition of inverse. So we can sometimes talk about the function or imagine what would be the pre-image, or how to calculate the pre-image of elements in B. So we can, if f of x is equal to y, then we can define y as a certain function f prime of x, okay? And then this f prime is a candidate to be an inverse function, but we cannot use the word inverse unless f itself is bijective, okay? So we may call it the reverse of that function, or the pre-image function of f, something like that, okay? And particularly when f is described with the formula, then we can use certain math magic to find the relation in the other way around, to define each y as a function of x, the pre-image x. So for example, for x squared, we know that we have a magical function called the square root, but of course we have plenty of constraints on it, okay? So we have to restrict the domain, etc., so to make sure that that this function, square root function, is really definable over the domain and codomain, okay? So this is what I meant actually. So if this function invertible, well, it's not if we define it over R to R, but if we define it from R plus to R plus, then it's definable. Okay, so yeah, but we know that somehow a certain f prime of x yields, okay, yields y actually, okay, or sorry, I wanted to say that f prime of every y would yield x from it, okay? But for example, f prime of x squared, to get it back to x, well, it's a piecewise function, okay? It depends on the value of x, whether it's positive or negative, okay? So it's not a well-defined function in the sense that we defined earlier in these slides. So we talk about the inverse of a function only when the function is a bijection, okay? Good. Now if we restrict the domain to R plus and the codomain to R, then yeah, it's still actually not invertible, because all these elements would not have in the codomain would not have any image in the domain. But if we restrict both the domain and the codomain to R plus, well, then in this case the function is invertible, and every element in the codomain has exactly one pre-image, and then the f minus 1 inverse function is definable. Okay, so let's switch to the other topic, which is composition. Composition over two different functions is defined in case the first function goes from a certain domain A to a certain codomain B, and the second function applies to the domain, the codomain B as its domain to the new codomain C. Okay. So we need at least to have the range of G. It means all the set of images of G in B to be part of the codomain to be subset of the domain of F. Okay, so we could define as F going from S to C, but S must contain F of A. Okay, the range, G of A, the range of the function G. Okay. so that the composition in this case is definable. Okay, we call it f round g, okay, or f of g of x. So the composition of f with g denoted by f round g is the function from a to c defined by f of g of x. We say f of g or f composite g or f round g, and we can depict it in this way. So we map every element in A to its image by G in B, and then every element here to its image by F. And now we can talk about the image of elements in A in C by F composite G, okay, by F around G. Okay, so the elements in C would be images of elements in A if there exist elements in B here such that the image of those elements by F is equal to that element in C, and those elements here are the images of the elements in A by G. So note that the composition cannot be defined unless again, the range of G is a subset of the domain of F, okay? So if this domain is not particularly B, if it is simply a certain domain S, we need at least to make sure that G of A, the range of G, is a subset of that set S. An example. So here we have these elements wxy to be the range of A, and we have this function f here, okay? So we could actually define f from G only on this subset. This is the minimum required, but if we define it for more elements, then it's not a big deal. We can now talk about f from G to be this function here. Okay, so the image of A by f round G would be tech, one step, another step, and then we have G. So it's still unique. It's still unique because every element G has, every element in B has exactly one image, and every element in A has exactly one image. So we can use these two steps to make sure that every element in A has finally an element in C. Okay, so this is why we can make it for sure that the f round G of A is equal to J. So it's we can write it this way. Sorry, or we can also write f of G of A, and then you can reason about it step by step. So well, this is equal to f of the G of A is equal to Y, and the f of Y is equal to J. So this is why the f round G of A is equal to J. Okay, and you can do the same for all the other elements. Good. So suppose you have these two functions defined by the formulas f of x equal to x squared and g of x equal to 2x plus 1. Well, the f of g of x would be equal to 2x plus 1 squared. Okay, so and g of f of x would be defined as follows. It's 2x squared plus 1. So I think you are already familiar with this concept. A couple of questions in this example. So let G be the function from the set ABC to itself, such that G of A is equal to B, G of B is equal to C, and G of C is equal to A. And let the function f map the elements a, b, c to 1, 2, 3 in this way. So f a b 3, f of b equal to 2, and f of c is equal to 1. Then in this case, what would be the composition of f and g? Okay, and what is the composition of g and f? So f from g is definable because actually g goes from a to a, and then G, so we can write it in this way. So G goes from A to A, and then F goes from every element in A, to every element in, let's call this second set B, okay? And But the other way around, it's not possible. Okay, so to talk about G round F, okay, it's not possible because the images of F, so F goes from A to B, okay, so the range of F is this set here, 1, 2, 3, which is not a subset of A. So we cannot go with any function that such as G, because okay, so G goes from A to A. Okay, so we cannot do this. We cannot do the mapping from B to A. G is not defined on the domain B. Okay, it's defined on the domain A. Good. We end the discussion of this part with few particular functions, such as the floor function, the ceiling function, the factorial, and the piecewise functions. So the floor function, denoted by f of x equal to floor of x, is the largest integer less than or equal to x. So what would mean, we will see it in a example just right after the definition of the ceiling. The ceiling is defined as the smallest integer greater than or equal to x. So we can see it with decimal numbers. So the ceiling of the 3.5 is equal to 4. Okay, it's look at it. It's the smallest integer that is greater than or equal to x. Okay. So 5 is also greater than or equal to 3.5, but it's not the smallest integer that is greater than or equal to 2. Okay, and the 3 is smaller than x. We need the smallest integer that is greater than or equal to x. What about the floor of 3.5? Well, this is equal to 3. Okay, because this is the largest integer that is less than or equal to 3.5. Okay, 2 is also less than or equal to 3.5, but it's not the largest integer. So I like to see them in this way. So if you have certain integer n and plus 1, well, x would be somewhere in between. Okay, in this case, this is equal to the floor of x, and this is equal, I'm sorry, we put nothing on the top, so this is equal to the floor of x, and n plus 1 would be equal to the ceiling of x. Okay, it's also a nice approach to put the n plus 0.5 plus half here, and to put all the possible cases for x. X could be here exactly in the middle, a little bit after the half, or a bit before the half of the interval between n and n plus 1. This is really helpful when you do the proofs about the ceiling and floor functions. So just draw all the possible cases. For example, to reason about 2 times x, okay? Well, you have 2 possible cases, whether x is less than or equal to half after n, or greater than or equal, or strictly greater than the half, okay? We will see it in one of the examples. The same applies to negative numbers, except that yeah, the ceiling would be the it's always the same definition, but it would be a in absolute value a smaller number. Okay, so the floor of 1 minus 1.5 is equal to minus 2. Okay, and the ceiling is minus 1. Okay, so we just inverse the it's quite simple because we have negative numbers. Okay, so expected. And we can also map them as a graph, so you can see it in this way. So you have these open intervals here. So everything starting from n plus epsilon, okay, up to n plus 1, its ceiling is equal to n plus 1, and vice versa. Okay, so everything from n plus 1 minus epsilon, for every positive epsilon, its floor is equal to n down to n itself. Okay, so you have the dual case between the floor and the ceiling. Okay, so you can see it in this way too. It's quite similar to what I wanted you to see with this representation on the x-axis. You have this table of properties. I think most of it can be proved by hand, but you can also take it for granted and use it in your proof. So you have a couple of examples in the slides. So, well, this definition here is, or for example, this first property and then even the second one, they stem from what I drew on the axis a few slides ago. This one stems from the duality when you go to negative numbers. So I think most of them are quite straightforward, and you can check them on your own as properties, or you will use them actually in your proofs later on. So let's consider one example. So we want to prove that if x is a real number, then 2 times x, the floor of 2 times x is equal to the floor of x plus the floor of x plus half. Okay, so often you will proceed with a proof by case. So what you can imagine about the value of x is that is equal to a certain integer plus a certain value epsilon, where epsilon is greater than or equal to 0 and strictly less than 1. So it's really somewhere, because we're working with the floor, so we're gonna take everything from a certain natural integer n itself and included and up to n plus 1 excluded as an open interval. Okay, so we can use this notation here. Okay, what we use to represent in this way with parentheses and brackets. Okay, so so this is what we mean by this n plus epsilon, where epsilon is between 0 and 1. So depending on the value of epsilon, whether epsilon is strictly less than half or greater than or equal to half, we will have different facts, okay, about the floor of x. For example, 2 times x is equal to 2 times n plus 2 times epsilon. Epsilon is strictly less than half, so 2 times epsilon is still something between 0 and half. So we imagine that you consider a number such as 3.3 or 3.4 or any combination, as long as it's strictly less than 3.5. Okay. Well, in this case, if you multiply this number by 2, you won't reach 8. Okay. So if you look at x plus half, okay, so the floor of it would be equal to n, because it's equal to n plus half plus epsilon, and half plus epsilon is still something less than 1. So because epsilon is strictly less than half. So in this case, the floor of 2x is equal to 2n, and the floor of x plus the floor of x plus half is equal to n plus n, which is equal to 10. So they are equal. Okay. The other case is when epsilon is greater than or equal to half. So clearly, when you have like 3.5 and 3.5, yeah, I'm sorry. What I wanted to say here, that your number would be strictly less than 7, guys. So if you have 3.5, 3.5, well, you end up having 7, and it can grow more than that. Okay, so but still, actually, this would be equal to the floor of x plus the floor of x plus half for the following reasons. So 2 times x would be equal to 2 times n plus 2 times epsilon, which is 2n plus 1 plus 2 epsilon minus 1, and 2 epsilon minus 1 would be strictly less than 1 in this case. Okay, it's greater than so epsilon, 2 times epsilon itself, it's greater than half. Okay, 2 times epsilon is greater than or equal to 1, but 2 epsilon minus 1 would be less than or strictly less than 1. So we end up having this fact about the floor of 2x. Okay, it's equal to 2n plus 1. The same applies to x plus half. So now we are adding half to epsilon. So to this inequality, epsilon greater than or equal to half, we will also add half on the right hand side, and we'll have epsilon plus half is greater than or equal to 1. So which means that epsilon minus 1 minus half is the floor of n plus half plus epsilon is equal to the floor of n plus 1 plus epsilon minus half, okay? And which is equal to n plus 1, since we have this formula here, okay? This inequality. And yeah, in this case, we end up having floor of 2 times x is equal to n plus 1 plus floor of x, which is always n, and the floor of x plus half, which is n plus 1. Okay, so in both cases, actually, we have the equality maintained, and this is why we can conclude that this original equality holds. Okay, so you will have similar exercises and they practice that, so you can refer to the definitions or this table here or this example, okay, the example of that you have in this slide number 32, or the table that you have in slide number 31. What about the factorial? We just want you to recall that it's equal to the product of all the integers up to n, positive integers. So it's equal to 1 times 2 times to n minus 1, including n. And by definition, the factorial of 0 is equal to 1. The factorial of 1 is equal also to 1. The factorial of 2 is equal to 1 times 2, which is 2. Factorial of 6 is a very big number already. Okay, it's a big number, 720. And factorial of 20 is a very, very large number. Okay, so when we will study algorithms, we will be interested in knowing how much time and how much effort a certain algorithm will be doing at a certain moment, and this is why we will count the number of iterations or the amount of work that a certain function or algorithm is doing while handling its input. And in certain cases, the effort would be a function of a factorial function of the input, and which means that your problem is really hard. Okay, for an input of size 20, you're doing this amount of work approximately. So yeah, so we will use it later on, and eventually we'll use it also in the exercises. Of course, we have a certain formula to approximate the value of the factorial, and this is also helpful to be able to compare the factorial of n to other polynomials of n. The last part is about the piecewise functions. So these are functions that are split into different subfunctions on different parts of the domain, just to make them functions finally on the whole domain. So the function would behave differently based on the values of the input value x. So one of the famous piecewise functions is the absolute value, f of x equal to the absolute value of x, where this is equal to x if x is greater than or equal to 0, and minus x if x is negative. Okay. Yeah, so I think this was the last slide for this part, and in the next part we will start talking about the cardinality of sets and how can we use functions to actually particularly bijective functions to reason or to compare cardinalities of sets and to reason about the size of sets.